at the upper and lower bounds. We talked at the end of the hour yesterday about the fact that, you know, eventually these go to either positive or negative infinity. And so we can look at our answer in synthetic division, and sometimes that answer will give us a clue if it's now going to positive infinity or it's now going to negative infinity. And if it's going to go to positive infinity from that point on, I don't have to try any larger numbers to kind of find that to find where zeros are. So just a reminder, if this is in x minus c form, so we're dividing by c, x minus c is the potential factor, and c is the potential zero. And so the deal here is if c is less than or equal to 0, so we do have to be on the left side of that x-axis. And the last line is alternately non-negative and non-positive. So 0 can kind of, you know, go either way. Then that's a lower bound, and we don't have to try anything lower than that. If c is greater than 0 and that last line of synthetic division is non-negative, then it's an upper bound and for the real zeros, and we don't have to go any higher. One thing I'll say, and sometimes I do alternate, you know, try a positive 1, negative 1, positive 3, negative 3, whatever the case may be. But there is a certain value in just trying positive 1, then positive 3, then positive whatever the another one is, so that you're kind of more attuned to that pattern that's happening. And you are, at this point in your life, allowed to graph the function to determine intervals in which the zeros lie, and then use synthetic substitution to confirm that you have upper and lower bounds, and the rational root theorem to help you find the zeros as you go. So now we're going to do some problems and excuse me, and look at those and look for those zeros. So it says determine an interval in which all real zeros of f of x equals x to the fourth minus 4x to the third minus 11x squared minus 4x minus 12 must lie. And then explain your reasoning using the upper and lower bound test. So first we'll graph that, and you're capable of graphing, so I'm going to show you the graph. Here's a graph of this as we go, and we'll look at the graph. We'll also look at P over Q. So this is number 4, and our rule is f of x is x to the fourth minus 4x to the third minus 11x squared minus 4x minus 12. And so we need to figure out what P over Q is. And P, Lewis, is the factors of what? 12. And Q is the factors of? So what's the coefficient there? 1. So will we have any fractions in this choices for rational roots? No. And I don't know if you paid attention, but on this these tests for the intervals, the upper and lower bounds, that's talking about real numbers that this is between, and we're looking at P over Q, which is rational numbers. So the first thing we're going to do is just list out P over Q, so all of the factors of 12. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Plus or minus 12. And I think that's all of them. So those are all of our numbers that we're looking at. Now we'll decide on the upper and lower bound visually, but we'll validate that using the upper and lower bound test. So we'll kind of say, it looks like it's between here and here, and then we'll use the closest numbers to that. So it appears as though really kind of after, you know, maybe this is -2, we're not sure. So I would say the boundary, and you might just sketch this down along here, the boundary that I would use is -3. And then here, 1, 2, 3, 4, 5, 6, 7, I would use the other boundary as 7. So I do want to go past them a little bit just to be sure, because I'm not 100% sure if that's going to hit at a grid point, just a little over, just a little under, and I don't want to, miscalculate that. So I think that I'm going to try -3 and see if that is a lower bound. And so I'm just going to do synthetic division. Since it's my first synthetic division of the day, I'm going to use the longer rule for the lower bound, and then I'll use the shorter rule for the upper bound just to see. So I think -3 is going to be my boundary. So -3 and 1, -4, -11, -4, -12, 4, 3, 2, 1, 0. I've got everything accounted for. So I'll bring down my 1, -3, -7, 21 minus 11 is 10, -30 minus 4, -34. Negative 34 times 3 is positive 102 maybe. And then minus 12 is 90. So really what I want to look at here is my bottom row. And in this case, I have positive, negative, positive, negative, positive. And so this can be considered a lower bound. My next number is -2. I could try that to see if that is also a lower bound. But at least now, I have now eliminated, I don't have to try -4, -6, or -12. I know that they are not going to work. And so that's what this boundary, kind of the power of that boundary. I now know I don't have to try, so I can omit from my P over Q -4, -6, and -12. None of those are going to work. And then I'll try, excuse me, my upper bound. I think I said that was 7. And this time I'll do the shorter version. So, we just kind of are seeing both of those again. -4, -11, -4. So, a question on this? Okay. Okay, and since I think my upper bound is +7, and I might need a little help with this one. Boy, maybe I shouldn't have done this one this way. So I'm anticipating that, especially because I see that my graph is going up, I'm anticipating these to all be positive, correct? And if that's the case, it is the an upper bound that I can use. So I'll bring down my 1. 7 minus 4 is 3. 21 minus 11 is 10. 70 minus 4 is 66. And you know what? I'm not sure what 66 times 7 is, but I'm sure when I subtract 12, it's going to be positive. Do you agree? So I'm pretty confident that I can kind of say that. So then when I look at this row, it's positive, 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 positive. And so since everything is positive, or non-negative is the word we used. So let's pretend a minute that 10 was a 0. That's still not negative, correct? So even if somewhere along here there's a 0, that is okay. So this is the upper bound. And so now I know 7 is as high as I can go. Yeah, 6 is right here, but I can now omit 12. And think about end behavior that we've talked about over this year so far. Remember that end behavior, if it's even and positive, it's going to go like that in the end, right? So remember those wrinkliness, and so the zeros are going to occur relatively close to the y-axis. So that's one of the reasons I alternate positive and negative, because if there are going to be rational roots, they're generally going to be a little on the closer side. So, you know, I would never start my synthetic division with like the 12 or the negative 12. I always start with kind of the closer to zeros and kind of thinking about that. Now, excuse me. So now I know what my possible zeros are. I looked at that graph, so I have some ideas of things I might try. And so now I've eliminated some things. Now I'm going to try plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Oh, excuse me, plus or minus 1, plus or minus 2, 3, 4, and 6 are my kind of candidates. When I looked at it, it looked like negative 2 might have been a 0, so that's the next one that I'll try. So my upper and lower bounds, so my upper bound is 7, and my lower bound is negative 3. Now, you have the luxury of using a graphing calculator to kind of figure that out. As you get further along in mathematics, you're not going to have that graphing ability. So what we usually do with these upper and lower bounds is we just are kind of keeping an eye on these rows as we get them. And if we start getting, oh look, they're all positive, then we know that we've kind of hit that upper bound. Or oh look, they're alternating, so we know we've kind of hit that lower bound as well. But by our graph, you know, I'm going to try right next to that lower bound, I'm going to try negative 2. I'm going to try positive 6 and kind of see what happens there. So let me write my numbers again. 1, negative 4, negative 11, negative 4, negative 12. And I'm just going to use my short version. So negative 2, 1, negative 2 minus 4, negative 6, 12 minus 11 is 1, negative 2 minus 4, negative 6, 12 minus 12, 0. So there's a 0. And now that I have a 0, what am I going to do if I'm using my short version? Cross off what? Yep, I'm going to cross off the 0, and now, and I generally also kind of cross this off. I'll cross it off in like a purple, so my eyes aren't drawn to it. And now I'm just going to use this row, and I said that 6 looked like a good candidate. I'll try that and kind of see what happens. So I bring down my 1. 6 minus 6 is 0. 0 plus 1 is 1, 6 minus 6 is 0. So that's another 0 or root. And then that leaves me with this. And as soon as I'm down to 3 digits, that's a quadratic. Do you agree? And so once it's a quadratic, really, you know, why go through all these other things? Once it's a quadratic, I'm going to maybe just write that. So this is 0, 1, 2, because that's a 0. X squared plus 0x plus 1. And is that factorable? No. Are the zeros real? Because set this equal to 0 in your head, and you're going to get x alone. Are the zeros going to be real? No, but are there 2 complex zeros? Yeah, so down the road, we're going to have to get those zeros too. But in this one, we're not asked for that. So then, you know, I'm just going to kind of write a little summary of what I found. So my upper and lower bounds are from, was it negative 3? Yep, negative 3 to 7 by those boundary tests. And I will say, if you're telling me what the upper or lower bound is, you need to validate that by showing me how you got that. And then my real zeros are -2, and +6. Those are the ones that worked. And we know that the other zeros will be complex. So at this point, we're not interested in that. So that's the upper and lower bound test. Now, that's not the biggest test that we use. The biggest test we use is Descartes' rule of signs. And mathematicians love to have things named after them. So Descartes is who came up with Descartes' rule of signs. And what he found is that by looking at the original rule and kind of counting how many changes of signs there are, we can make some determinations about the zeros or the roots. Now, do you remember a minute ago I just said, remember x squared plus 1, it's irrational or complex, right? And there's 2 of them, right? Do you agree that complex roots have to come in pairs, right? And they come in conjugate pairs, 1 plus 3i and 1 minus 3i. And that way, because think about this, this has complex zeros, but it has all not only real, but like it has all integer coefficients, right? For each term. So there's no i's in here. So if you have an I as a 0, you have to have its conjugate pair. So when you multiply those, the i's drop out because you get I squared and the other i's drop out. So I want you to keep that in mind as we go to this next thing. And we're just going to look at this. How many changes of sign are there? And just a second. So we should notice that there is 1 sign change here, and we got 1 positive real root. And so now we'll look at this rule. And this is Descartes' rule of signs. And it's kind of trying to eliminate or trying to decide how many zeros or roots there are. So Descartes' rule of signs says this: if f of x is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0 is a polynomial function with real coefficients. Actually, you want to know that because that is important down your road. Then the number of positive real roots is equal to the number of variations of sign or less than that by some even number. So heaven forbid that there were 12 changes in sign. That means there could be 12 positive roots, there could be 12, there could be 10, there could be 8, 6, 4, or 2. So now you can see why I'm happy if I get 1, because if it says if there's 1 sign change, there is only 1 positive real root. And it's real, not rational, but it gives us something to go with. And so if there were 3 sign changes, there could be 3 or 1 positive root, right? And what if there are no sign changes? What if there are no sign changes? Then there are no positive roots. Does that make sense? If there's no sign changes, then there are none. And so anytime we get no sign changes either here or there, we can eliminate half of our choices of P over Q, right? Because if there isn't, so my favorite answers for Descartes' rule of signs is 0 and 1. Because either 0 means just eliminate all the positives or all the negatives, whichever it happens to be. And 1 means there's 1, so if I find 1 positive, I can quit looking at positives. So then the number of negative real zeros is the same as the number of variations of signs. And I didn't really emphasize this that much in the first one, but this has to be of f of negative x or less than that number by some even number. So we do have to put a negative x in for every value. This is just the original for the positives. And we have to put in a negative x and kind of go through and then see how many changes in sign that's going to give us, and then we can kind of go from there. So I see Descartes' rule of signs as much more powerful, especially because in practice, as you get into higher math, you're not going to have necessarily access to that graphing calculator to kind of visually look for those. So the upper and lower bounds, you're going to notice them as you're getting your answers, but you're really not going to predetermine them. Descartes' rule of signs, you're going to do immediately. P over Q, you're going to do immediately, and then our goal is to be able to find all of the zeros, and eventually all the complex ones as well. A variation of sign occurs in a polynomial written in standard form when consecutive coefficients have opposite signs. And make sure that it's always in standard form, right, from highest power to lowest power as we go through that. So here's this problem, and we're not at this point asked to do all of the work for number 5, and so eventually we'll put all these parts together, but right now it's just saying, tell us describe the possible real zeros. And so when we do this, we're just going to look at for the signs. So f of x is x to the 4th minus 3x to the 3rd minus 5x squared plus 2x plus 7. And we just use whatever terms we have, with no putting in zeros and all that stuff. So by yourself, just count how many changes of sign there are. Don't say it out loud. Huh? Okay, yeah. So make sure you didn't say it out loud. But now, what is it? You can say it out loud. How many changes in sign? 2. There's a brave soul. So here's this is positive and this one is negative, so that's a change in sign. This is still negative, so not a change in sign, but then this one's positive, that's a second change in sign. Now I'm positive, this is also positive, so that's not considered a change of sign. So there are 2 sign changes. And is this telling us about possible positive or negative roots? Which is it? Positive. So there could be 2 positive roots. What's our other option? 0. And so we just go down by 2 until there aren't any more. So there are 2 or 0, so it goes down by 2, positive. And we are going to write a real zeros. I'll just write zeros this time. So there's 2 or 0 positive real zeros. And so, the little bad part is when we do P over Q, that's rational zeros. So we could actually try all of our positive choices and neither of them work because they're both like irrational. But generally the kinds of problems that will be given will have the luxury of kind of generally something's going to work for us. Now, the next thing for the negatives, we have to replace f of x with f of negative x. So f of negative x, and I would suggest strongly that especially at first, you actually just put that in for the first couple problems so that you know what's happening. So this is negative x to the 4th minus 3 parentheses negative x. Oops, I didn't get my negative x there. Negative x to the 3rd minus 5 parentheses negative x squared plus 2 parentheses negative x plus 7. So I would suggest, looking at it, because sometimes in our minds, do you remember, if I say this, like if it's to an even power, it stays the way it was, right? It doesn't change. If it's to an odd power, it'll change to the opposite. And sometimes people, if you're not actually physically writing it down, you start counting those changes instead of the actual end changes. So a negative to the 4th is going to be positive. So this is x to the 4th. A negative to the third is negative, but then times this negative out in front is plus 3x to the third. Negative x squared is positive, but then it's minus 5x squared. Negative x times positive 2 will be minus 2x, and then the plus 7 just is not going to change for us. And you know, this isn't the most exciting problem. How many sign changes? 2. There are 2 sign changes again. Positive, positive, no sign change. To a negative, there's 1. Still negative, then to positive, so there's another one. So there are 2 sign changes for here, for the negatives as well. And so then our answer for this part is there are, again, 2 or 0, just going down by 2 every time. 2 or 0 negative real roots. Okay, now that's all those tests. So can you imagine that we're, you know, as we're doing these problems now, we're going to kind of put all of that together. We can eliminate some things. We can know if we have to look for, you know, positive and negative numbers. And so now we're going to look at the fundamental theorem of algebra. And you might be thinking, my gosh, I've had, you know, years of algebra now behind me. And I'm just getting to the fundamental theorem of algebra. Yes, that's why a lot of what you've done is considered elementary algebra, even though right, and elementary does not mean elementary school algebra, but it's elementary algebra as we go through and kind of consider what's happening. So let's see, there's this little extra thing. When using the Tarhart's rule of science, the number of real zeros indicated includes any repeated zeros. Okay, so that's a nice little disclaimer to know. So that's repeated zeros. Have we at all looked for repeated zeros when we've been doing this? No. So, you know, just keep that in the back of your mind that if 3 is a 0, you know, really you could try it again to see if it's a repeated 0. And so just kind of keep that in your mind as well. And now we're going to move to complex zeros. So that we just talked about it in a problem back there. Now, if we want to get all of them, we can just kind of find everything. So here is the fundamental theorem of algebra. And actually, the corollary is the one that, you know, I like the best. So, and I think we talked about corollaries yesterday, that, you know, that's just kind of a miniature theorem that follows the first one. So a polynomial function of degree n, where n is greater than 0, has at least one real or 1 0, real or imaginary, in the complex number system. So, you know, that is pretty vague. That's just saying any polynomial equation is going to have at least one real 0 in the complex number system. And so that's the fundamental theorem of algebra. But then the corollary is the one that is in my opinion more usable. So this is that a polynomial function of degree n has exactly n zeros, including repeated zeros, in the complex number system. So in the complex number system, so if we allow ourselves to go beyond the real numbers into the complex numbers system, if it is a 5th power equation, polynomial equation, it has 5 zeros. If it's to the 12th power, it has 12 zeros. Some of them might be complex, and they come in conjugate pairs, but they're going to be all of those. So then now that we know this, we can kind of be a little bit more specific about factoring things. And so what we're going to next have is the linear factorization theorem. And so the linear factorization theorem says if f of x is a polynomial function of degree n greater than 0, then f has exactly n linear factors. It has exactly n linear factors. If it's to the degree 7, it has 7 linear factors. And remember, we can always multiply by some number out in front, like multiply everything by 2. And so that is f of x equals a sub n. And a lot of times a sub n will just be 1, and times x minus c1, x minus c2, dot, 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 x minus c sub n. So we're subscripting all these, and that's helping us determine how many there are. And this would be a common factor. And do you agree when you're finding zeros, a sub n has no bearing on the answers, right? Because, like, if I have 2x squared plus 4x plus 8, I'm going to divide out that 2, common factor of 2, and it's not going to have any bearing on my answer. Where a sub n is some non-zero real number, often 1, and c1, C2 through Cn are complex zeros, including repeated zeros of f. And I want to remind you that complex numbers are a plus bi, right? So a plus bi is kind of the general complex number. And so if a is 0, it's a pure imaginary number. If b is 0, it's a real number. And so when we say complex zeros, that does not mean every zero has I in it. It just means that we can consider them in the complex number system. The complex number system counts every number. Let me think if I can make this statement. I'm pretty sure every number you're familiar with at this point in your life, the complex number system. All real numbers, all imaginary numbers, all complex numbers, rational, everything that you would have. And then according to the conjugate root theorem, the if we have a polynomial equation in one variable with real coefficients, so if we have a polynomial equation in one variable with real coefficients, and it has a root of the form a plus bi, where b is not 0, so it does have the I in it, then its complex conjugate, a minus bi, is also a root. So this one you want to know super well, and here's why. The book authors, excuse me, the book authors will give you a complex root, and you have to know that its conjugate pair is also a root. And you'll be writing possible polynomial equations for that, okay? So that's what we're going to do next. Do you have something written down about this? Because you want to know this. And this next part seems to be a little hard for students, but you are very well versed in this information. So we'll start with kind of a real number problem. Okay, so first I'm going to ask you a bunch of questions. So if I was told that just the roots of a polynomial equation, I'll make it pretty small. So 3 and -2 are the zeros. Write this down, and then write the factors. And Thomas, what did you write as factors, or what should you write as factors? What's a factor? So I want the two factors. If the 3 is the root, I'll give you the first one. X minus 3 is a factor. What's the other factor? X plus 2. So if I'm told those roots, I can get the factors. If I'm told the factors, I can multiply those out and get a possible quadratic equation. In this case, x squared minus x minus 6, right? Foiling that out and combining terms. Do you agree? So that's a possible rule with these zeros. Does everybody agree with that? Now, I'm going to make up another rule. 5x squared minus 5x minus 30. Do you agree that's another rule that has exactly those roots or zeros? Correct? What did I do? I just multiplied it by 5. So if I was going to factor this, I would make it into 5 times x squared minus x and minus 6, set it equal to 0, and then I would just factor it further and everything would work out just great. Now, I'm going to pretend for a minute that instead I'm told that my root is 2 plus 3i. Is that the only root? No, because they come in what? Conjugate pairs. So the book authors are only going to tell me one. I have to know. So the conjugate pair is 2 minus 3i. Now, writing these as factors is a little trickier, and multiplying them is also a little trickier. So when I write this, think about what we did here, x minus that root, right? And x, really, this one would have been x minus that root. Do you agree? But we just automatically change that in our head, right? So when we write this as conjugate factors, you should be writing this down because we go to harder ones immediately after this. So if I'm going to write this in factored form, I'm going to write x minus 2 plus 3i. And my other factor is going to be x minus, parentheses, 2 minus 3i. So that's a trickier first step. With numbers like 3 and negative 2, I can just pop those in there and I can change the sign in my head. But here, that is not a wise move. So now I'm going to distribute my negatives and I'm going to get x, parentheses, x minus 2 minus 3i. And then I'm going to get as my other factor x minus 2 plus 3i. And notice the minus 2 stayed the same because it was a positive 2. Just like when it's a positive 3, it's a minus 3. But the 3i becomes a plus 3i and a minus 3i. And that should make good sense to us because when we multiply that out, our i's should all drop out. And then we'll have I squared 3 or minus 9i squared at the end. And that'll be plus 9, right? So, and we've multiplied these before. So we're going to get a bunch of terms because we're going to take x times each of that. That's 3 terms. Negative 2 times each of those, the 3 more terms. Negative 3 times all those, that's more terms. But guess what? In the end, it's just going to be a quadratic equation, right? So x squared plus something x plus a number. Got it? Okay. Do you feel a need to multiply that out to see, or are you good at that? You have to tell me right now and be honest. Not good? Okay. So I'll ask you to help me with that. Austin, just take the x and distribute it times everything in that second one and just tell me what you get. I might have to write on 2 lines. Okay. And then Megan, multiply the negative 2 times all of those. multiply this -2, and I'm color coding it, so multiply that -2 distributed into that second one. Okay. Oops. And then I'll use red, and I have to use the second line, but really it's just all kind of out there. And Janet, help me multiply -3i times each of those. I think plus. Yeah, there we go. And so now, and if this doesn't make the i's drop out, I would go back because I made a mistake someplace along here, right? Because the i's have to drop out because this is going to have real coefficients. First thing I would do is make that +9. The next thing, I'll just kind of cross out any of the things that have i's in them, if I can. So 3ix minus 3ix, those get rid of minus 6i and plus 6i. So again, and look at them carefully, because if they didn't cross off, you know, did I make a mistake in just multiplying them here, or maybe I made a mistake up there as I went through. And then our equation is x squared minus 4x plus 4. And so this, oh, +9. Yes, thank you. So x squared minus 4x plus 13. Thank you very much. So that's what's happening here. This, if I did this using like P over Q, by the way, P over Q would be ±1 ±13, right? So there's not a lot to try there. Descartes' rule of signs, how many sign changes? 2. So there's 2 or 0 positive real roots. And how many, well, we won't even go into the negative, but we could use some of our other things. So this is our next problem. The book authors give us some zeros, and we have to come up with a polynomial function in standard form that has of least degree with these zeros. So this is number 6. Given zeros, and our zeros are -1, 2, and 2 minus I, write the polynomial. And I'm using 2 colors here on purpose because that is all we're told. So we know if there's a complex 2 minus I, there's also another one, 2 plus I. And the book authors aren't going to tell us that, but we also have 2 plus I. And I'm not going to tell you, the authors aren't going to tell you, you are expected to know, okay? So that's what you're expected to know in this kind of problem. And now I'm just going to write the factors, and I'm going to write, how many factors am I going to have? 4, right? I'm going to write the 4 factors, and then I have to do all this multiplying as I go. So I'm going to write them in an unusual way. You know, we would write x plus 1, correct? But I'm just going to write x minus -1 because I've got so much work to do. X minus 2, x minus parentheses 2 minus I, and x minus parentheses 2 plus I. And just to kind of illustrate and make sure I know what's happening. So my next step is just to change all my signs. And then to be honest, I would multiply these two, right? I would never like do this and then this times this and then this times this. Because when I multiply these two, what is going to happen? The i's drop out. So I want to multiply those two. And personally, since I have 4 of them, I'd probably multiply these two, multiply those two, the i's drop out, and then multiply those two 3-term things. So I have x plus 1, x minus 2, x minus 2 plus I, x minus 2 minus I. Pardon? Well, let's get rid of it then. If we don't like I, we'll just get rid of it. So the only like tricky part for me is kind of making sure I have all my parentheses. So I'm going to FOIL this out, and to be honest, I have enough work to do over there. I'm just going to write the answer here. Are you with me on that when I do that? Yes or no? Like, you know, so x squared minus x minus 2, right? And you can all just get that. Because this one I'm just going to have to like work a little bit harder at. So let's do this, and I'll color code again. Eli, why don't you distribute the x times this second one? I'll call it ix because I started the I already. Ashton, multiply -2 times all that stuff. Yep. And the last one, Luke, go ahead and tell me that one. Plus ix. Minus I squared. And so now I'm just going to do lots of cleaning up. I have minus ix and plus ix. I'm happy with that. I have plus 2i and minus 2i. I have my minus I squared, which is plus 1. And so I'm just going to leave my first 3-term thing as x squared minus x minus 2, and I'm going to try to clean this one up all together. So that's x squared minus 2x and minus 2x, so minus 4x, and plus 4 and plus 1 is plus 5. Okay, and I'm just going to check my notes because I hate to make a mistake and then have all that happen. So now, essentially, I do the same thing again, right? Oh, we will do that tomorrow. Have a good day.